Hello and welcome. If you've been watching the previous videos, you know I've been trying desperately to get my assembly language code to call the basic random function so I can get some random numbers and print things out. And I ran into a couple of snafus, but those are all fixed, and I am feeling much more like myself now. So now we're ready to watch this code in action. Just a quick warning that this is a bit of a longer video than usual, but don't worry, I saved all the most boring stuff for the end, and I'll let you know when that's coming up so you can tune out early. Anyway, fasten your seatbelts, it's going to be a crazy ride. Let's go! So we start, as always, in Color Basic Unraveled, and it tells us about the R&D function as called by BASIC. And this is what I want to call to get some random numbers for my assembly language code. There is, by the way, no quick summary of this like there is for many of the other undocumented subroutines. This is basically it. There's no like two-sentence summary like they have where they tell you, this is the input, this is the output. So you kind of just have to read this, but luckily there isn't really much to know. If you read it just a little bit, you'll see the input is FPOW and the output is FPOW. So as long as I understand how to deal with FPOW, I'm cool. And this is what sent me on the journey in the first place to understand the floating point accumulator, and then later converting the accumulator into strings and so on and so forth. But even so this makes it seem obvious, I'm curious if there are any instances where R&D is called. So let's just do a search here. R&D. Stuff used by R&D. These are just some pieces of data. That's not a call. And this is just a dispatch table where that's one of the entries. That's it. We're pretty much on our own. But then that opens another question. How do you distinguish between code that properly generates random numbers and code that is just generating numbers from some bizarre, incorrect, accidental procedure that doesn't always result in the same result? How do I know I'm really getting random numbers and not just some garbage that happens to be changing? Obviously, one cannot completely mathematically prove that you're correct, but what one can do is gain a little bit of confidence by generating statistics. So if I can generate a count for each random outcome and verify that the counts are roughly equal, then that means the distribution of answers should be indicative of whether I'm really getting random numbers or not. So the op I'm going to run is going to use these as the input bytes for the floating point accumulator to be used by R&D. So these bytes, the exponent, mantissa, and sign, will be equivalent to the integer 16. So that means it's like I'm passing 16 to R&D, so I should be getting random numbers from 1 to 16. What I'm going to do is print out how many times each of those numbers gets chosen. And I'm just going to loop and loop and loop. What you're looking at is kind of like those old pages in the back of the Color Basic, Extended Color Basic manual where you're trying to map out how you'll use the screen. So if you look, you'll see we have 32 columns, we've got 16 rows, and so I'm kind of mapping out what I want to print on the screen and where. So going down here on the left-hand side, these are the stats. Here I'm going to show the random number that actually got generated. The code to call R&D is really not much, especially if you've been keeping up and watching the videos. You've seen code that looks a lot like this before. All I'm doing is populating the floating point accumulator, populating the exponent, mantissa, sign, and I'm clearing out the other 7 bytes that I still don't know what they do. And I'm populating it with those 3 values I showed you that are equivalent to decimal 16. When that's done, I just jump to rand. Once RND returns, I can expect that the answer will be in FPAL, and so I can go ahead and copy it to some safekeeping so that I can do some other things. I'm not going to talk about this just yet, but I'm going to be printing it out and I'm going to be checking out the stats and stuff, and then based on what I see, I'll have an idea of whether it's working or not. The parts of this code that I want to focus on are really just the parts that use the basic ROM routines, because that's really what this sequence of videos is about. Later in this video, after everyone has fallen asleep, that's when I'm going to be talking about basically all the rest of this code. So we've talked about the fact that I call RND. I mentioned briefly that what's going on here is I have another area of memory set aside to keep a copy of this. Because FPAL tends to be overwritten every time it's read, I want a safekeeping place to keep that FPAL in case I need it for another purpose, which I will be doing later. So all this is doing is copying it elsewhere so that later I can copy it back and reuse it. So after I've made a copy, the first thing I want to do is print the number I got back. So the first thing I do is I convert what's in FPAL, which is now the random number, as a floating point representation, into an ASCII string. And you've seen me do this before on a previous video, and so you know that ends up in strbuff +3. So once that returns, I can have my X point to that string. I can have my Y point to wherever I want to print it in the screen buffer. And then I have a routine that will just print that string. The other thing I want to do is to figure out which count to increment. So if I got a 1 as an outcome, I want to increment the count associated with 1. If I got a 15 as an outcome, I want to increment the count associated with 15, and so on. So I have a stat table. It starts here. There are 16 entries, and each entry has 2 bytes. So I want to store a 16-bit number to count how many times a particular outcome results. And then I just have another symbol that tells me when I'm at the end of the table, so I can be lazy and not have to do any math later on. So now we're back here. I restore the copy of FPAL back to the actual FPAL address that BASIC expects to find it at. And I do these 2 things so I can convert that floating point number to an integer. So clearing this means I'm expecting to get a value type that's numeric, and then calling this routine will convert whatever is in FPAL to the D register. And so the D register will now be holding my random number represented as an integer. I do a little range check, and then I save my B, because B is the low byte of D, and B should be the thing storing the entire random number. So my stack will look like whatever the return address for this was, followed by the random number chosen, B. And then I go to a routine that converts that number to an address into the stat table. And I'll show that code later after you've fallen asleep. So X will then point to the address. X is the address in the stat table related to this, related to the random number chosen. Now that I've done that, I can go ahead and get the count that X points to, add 1 to it, store it back. So now I've increased the stat for that one random outcome. And now I can go ahead and print that stat because I want to be printing these counts for everything all on one screen. GiveAb will take D and convert it back to FPAL. And remember, at this point, D is the stat. D is the count. So now FPAL will contain the count, which means I can then call this to get another ASCII string, this time representing the count. As you may recall, I called FPS convert before when I wanted to print the random number itself. So this converted FPAL, which contained the random number, to a string. Now I'm calling this to convert FPAL, which contains the count, into a string, so I can print that count. And then I go ahead and I print that count. So that covers the main stuff of this code, the stuff that interacts with the basic ROM. I will, after I show the demo, go ahead and run through all of the code. It will only be of interest to people who are interested in assembly language programming for its own sake, and not for the people who only care about the basic ROM, since the rest of this does not involve the basic ROM. So after I do the demo, feel free to turn it off. So here you see the actual random number that gets picked each time. And here are the counts. So for example, 1 has been picked 38 times, 5 has been picked 44 times, and it keeps going up and up and up. And what am I looking for is whether these numbers all roughly appear to be equal, especially as time goes on. The further and further I go, the more I should see the effect of the hopefully even distribution, and I should hopefully see these roughly being around each other. But since we're running this in an emulator, we can turn on turbo mode. So if you keep your eyes on these numbers, I think the effect will be most notable. There they go. Look at them go. And this does feel like it's doing things the way I wanted. Doesn't feel like there's an accident here. Now there could, in theory, be accidents, like this is not verifying that I'm not getting numbers out of the range. You know, I'm passing what I think is 16, but what if I'm not? What if I'm passing 18? How do I know it's not picking 17 or 18? So there is code to check for that, which I'll go over a little later. There's code to make sure I'm not going less than 1. But at this point, I think I'm pretty convinced that I now have code that is getting actual random numbers. All right. So this is the point where you should probably just stop watching the video. The rest of this is just going to be me going in excruciating detail through all of the code, whether it has to do with ROM or not. So I'm going to start at the bottom with the data. You've seen this before. This is the label that I present just before the random number that was chosen. It's just a string that we print. The stat table, as I mentioned before, 16 entries of 2 bytes each. This symbol tells us when we've reached the end of the stat table. And again, this holds the counts. So the first entry says how many times 1 was chosen. Second entry says how many times 2 was chosen, etc. These 6 bytes hold a copy of the floating point accumulator. This allows us to copy from the FPOW location that BASIC will stomp on at the slightest hint of asking it to do anything, and let us keep a copy so it's safe. And then we can copy it back when we need BASIC to use the value that we want it to use. Jumping back up to the top, we've got a bunch of equates to tell us where certain routines are. Val type is a location that holds either 0 to mean that we want to do a numeric conversion, or FF meaning we want to do a string conversion. I just need this to be cleared before I call int convert. So before I call this to convert what's in the floating point accumulator to an integer in D, it needs to see the val type is 0. Otherwise it's going to give me an error. Location of the floating point accumulator, first byte is the exponent, so that's that name. So always starts at 4F. And as I mentioned before, these are the values to tell it that I want a random number with 16 as the parameter. All right, let's start at main. First code that runs. First thing we want to do is initialize everything. So first, we load X with that label, the one that says R&D returned, and we tweak those lowercase letters as you saw in the last video. And just as a quick rundown, tweak lowercase letters, runs through a null terminated string, and anything that is within the range between little a and little z gets these 2 things done to it so that it will print as we expect. If you're curious what I'm talking about, take a look at the video just before this one. Next, we initialize the screen. Let's take a look at that. First thing it does is it clears the screen. Let's take a look at that. Clearing the screen involves starting at the location of the screen buffer start, taking 2 spaces, putting that in D, because D is nice and big and fat, and it can hold 2 characters at once. And we just stick D in every location in the screen buffer, starting here up until we get to screen end. Remember, these spaces will be the black spaces so that we can use the green on black characters. Once we're done with the clear screen, then we print the label for the random number. So this isn't printing the number itself, but the label. So I point X to the string, which has now been tweaked so it can be printed. This is the location in the screen buffer where I want to print. And as a reminder, plus 14 brings us right here. So it's going to print it out starting right here, RND returned. And then I bring that to print string. Print string takes what's in X and prints it at Y. Let's take a look at print string. It gets called a couple times. Print string has A run through the characters of X. So we start at X. A is the first character. Once it is 0, that means we're at the end of the string because we're assuming it's a null terminated string. And that's what this does. If it is 0, we're done. Otherwise, we put the character we read into the screen buffer that Y points to. We advance Y and we branch back up. You've seen this before. Now that we've printed the label for the random number chosen, we need to print the labels 1 through 16. That prints these numbers going down the side, and it prints these colons here. It doesn't print these changing numbers. So this time I let X point into the screen buffer, and I'm going to keep 2 registers to keep track of the numbers. I'm doing this kind of in a gross kind of way. So A is going to represent the tens digit, B is going to represent the ones digit, and they're going to be the characters. They're not actually going to be numerals that I'm doing real math with. These are the actual characters to be printed. So that brings me to my loop that will print 1 through 16. We ask if X has exceeded the screen size, and if so, we're going to get out of there. That's what this is going to do. We're going to skip to the next section if we're done. Otherwise, we store the tens digit where X is pointing. We store the ones digit where X is pointing. And then we just advance X to the next line. We increment the ones digit, so that's going to be this register holding that ASCII value for 1 or 2 or 3. And we compare it with the ASCII code for 9. If we're still in range, so if it's lower than or the same, then just go back up to the loop and keep on going, because we've already advanced the ones digit. But if the ones digit exceeded 9, then we have to increment our tens digit, and we reset our ones digit to 0. And then again, we go back up to the top of the loop and continue. This only works because I know the numbers that I'm doing. I'm not going beyond, say 99, for example. So this is really cooked up just to work for the case that I care about. When that's done, we go to print the separator. The separator is just that colon after all the labels. So I just have another loop to go all the way down the line with colons. And so we store the colon, we advance X to the next line, and we just loop. And then when we're done, we return. And that covers init screen. So bouncing back up, when init screen is done, then we init the stats table. This might be slightly more interesting, the stats table. So, although not really. So initting the stats table really just means setting it up with zeros. So in init stats table, we point X to the beginning of the stat table. We load D the 2 bytes with 0. And as long as we haven't reached the end, we store our 2 bytes of 0 and we branch and we loop. So that gets the stat table going with zeros. And then finally we can do stuff. So our main loop is just 2 instructions. Call random once and then repeat. Or let's look at random once. This is really where the real work happens. So in order to call random, as you've seen, we load the floating point accumulator where Basic ROM expects it to be with our special values to be 16. We call the random number generator. We save a copy of FPAL. I haven't shown you that code, so let's take a look at that code. So copy from FPAL and copy to FPAL basically need to do the same thing. So they both have in common this subroutine here. So let's look at this first. Copy fpal assumes that the source of the copy is pointed to by x, the destination of the copy is pointed to by y, and it also makes use of these other registers. So all it's doing is it's doing it 2 bytes at a time. Get 2 bytes that x points to, put them in y. Get the next 2 bytes that x points to, put them in y. Do that again. You do that 3 times. 3 times 2 is 6, and we're done. So this can be used in common both directions, whether I'm copying from fpal or to fpal. If I'm copying from fpal, the source is the basic ROM's floating point accumulator, and the destination is our own private copy of the accumulator. And then we jump here. You'll notice there's no separate RTS because I'm doing a jump. So since I'm doing a jump, the RTS from this routine will do the return for us. Opposite direction. Now I'm copying to fpal. So this is the part that's in common. Now the source is our copy. The destination is the basic ROM's floating point accumulator. And then we just fall through to this common routine that we just saw to do the copy. What I skipped over is kind of the boring stuff. I'm just zeroing out the rest. So those other bytes that we're not making use of, because I think they have to do with strings, but I don't really know whatever these things are. We're just zeroing them out so they don't interfere. So coming back up here, after we called the random number generator, we made a copy of fpal. And then, as I mentioned before, we convert that random number to a string. We load x with that string, we load y with the place to print it, and then we print it. We've seen print string, we haven't seen print string with pad. Print string with pad is really tiny. All it does is it calls print string, and then it adds 1 space as padding. And the reason is, let's say we print 12, and then the next thing we print is 3. This space will just overwrite whatever came after the last digit is that we printed. Here's probably the only really interesting thing in all of the non-basic ROM related stuff, which is the stat table. So first we take the copy of fpal of the random number and we put it back into the actual basic ROM's fpal. We clear out val type, which, as I said before, means that the conversion we're about to do is an integer of a numeric conversion. And then this converts the random number to an integer to be stored in D. And then we ask if it's in range. Is it in range? So let's take a look at this. And I'm actually going to demo what this thing does. So as I mentioned a while ago, we really want to make sure that the number we're getting is between 1 and 16 to verify that the code really works. So since D is supposed to be the integer representation of the generated random number, let's compare D with 1. If D is lower than 1, ooh, that's bad. Let's compare D with 16. If it's higher than 16, ooh, that's bad. But if we made it this far, we return and we're good. But if things are bad, we're going to freeze in place. So what that does is it shows us the random number that was generated, it shows us all the stats so far, and so we can look and see what the state is of things. Now you never saw this thing freeze, I didn't see this thing freeze, so either everything is great and we're getting numbers in range, or this test routine was insufficiently tested and doesn't really do what I think it does. So in order to test the test, let's see what happens if I change the low end of the check to 2. If that happens and they pick a 1, this will think it's out of range because 1 is not between 2 and 16, so it should freeze. So let's see what happens when I run that. And there you see pretty quickly it froze. And if we look here, we see sure enough the last random number printed was 1. And you can even verify that was the first one it encountered because nothing has been printed here yet. So it does seem to work on the low end. Let's double check that it works on the high end. So I'm going to change that to 1 and I'm going to change the high end to 15. So that means if it picks a 16, then it should freeze in place for that. here we go. It froze in place. 16 was the last thing chosen. So that takes care of freeze if out of range. What is the next thing we do? I really glossed over this before. But B so far has been the byte containing the random number chosen. So I'm pushing that onto the stack to save it, because I'm going to want it a little bit later on. And then I convert the number to the address. So whatever random number was chosen that's sitting in D, I want that to tell me the address in the stat table that I need to go to increment. Let's see how that works. So assuming B is the number that was chosen, we want X to point to the address in the stat table. So the first thing I do is I decrement B by 1, so we have 0-based indexing. That way 1 will become 0, and when we add 0 as an offset, we should end up at the very beginning of the table. We want to multiply B by 2 because there are 2 bytes per entry. So I'm going to do that with a mul command. A will have 2, B will have the 0-based index of the random number that was chosen. Mul multiplies A and B and puts the result in D. So A and B means 2 in B, and so that's what we get. Normally I would use something like a logical shift left, but on the 6809 we don't have a logical shift left D, and I want to keep this compatible with my hardware Cocoa, which is only a measly 6809, so I'm just doing it that way. So we start X pointing at the beginning of the stat table, and we just add D to the beginning, because D is now going to be going up by 2s based on which random number was chosen, and so we add that, and that becomes our final offset into stat table, and that's it. So now X points to where I want to find the number to increment. So now that this has returned, X points where I need it. I grab the count that X points to, I add 1 to the count that X pointed to, and I put that back into X. And while D holds that number, I can go and print it. So I will call givabth, which converts D back to fpal, and then I can call fps convert to convert fpal to a string. This is the thing I want to print, and then I can print it. Before I do that, I'm going to pull B off my stack. B, remember, what was on the stack, remember, was the random number that was chosen. I'm going to clear out A, and that means that the D register, which contains A and B, will be the random number chosen as a 16-bit number. And now I'm ready to go to print stat. So remember, I'm entering print stat with the string buffer holding the new stat entry that I want to print, and with D holding the random number that was chosen. Okay, so here we are at print stat. Since D is the random number that was chosen, it can tell us which line we want to print the new stat on. Remember, line 1 is if random number 1 was chosen, line 2 is if random number 2 was chosen, line 3 is if random number 3 was chosen, etc. So this is the formula to find the line. I take the random number that was chosen, I subtract 1, I multiply that by 32, and then I add 4. And if you look at my little cheat sheet here, adding 4, it's because of this. This is basically, these are the locations I'm trying to find. And since there's 32 characters per line, that's why I'm multiplying by 32 to get down to the line that I need to be at. So subtract 1 from B, put 32 in A so that I can multiply them together. Now D will contain that, and then I add 4 to get to the proper column. And now I'm ready to print that stat. So I set Y up to point to the screen buffer, and I offset into that whatever D has. So now Y is pointing to the exact location I want to print. Remember that the string buffer holds the stat that I'm going to print, so I point X there, and now I can call my routine to print X. So this is going to print that stat. And that's it. I hope you found this informative and interesting. If you check the description, there will be a link to all of the source code in this video, so you're welcome to try it out on your own. The road is not finished. I was not wanting to call RND just to call RND. There's stuff later to come that will make use of these random numbers. What could that be? Oh, only time will tell.